Welcome to the fifth lecture of the fourth week on the course in machine learning. In this lecture, we will talk about cluster analysis. So the agenda for the lecture is as follows. We will first talk about clustering analysis in general and say a few words about hyperparameters for this kind of algorithms, talk about distance measures, and then we will choose one form of categorization of clustering algorithms, actually 5 categories: partitioning-based, hierarchical-based, density-based, grid-based, and model-based. So there will be a short discussion about each of these categories. So cluster analysis is an important element in unsupervised concept learning. This means learning of multiple concepts from unsorted examples. Apart from being an important methodology for pre-processing of datasets in this unsupervised machine learning scenario, cluster analysis can be used as a standalone technique for particular categorization purposes. As instances are not classified in the unsupervised scenario, algorithms have to identify commonalities and structures in the dataset and to group the instances based on similarity. Then, when we found these groups, the detailed concept formation can continue, but then typically by using any of the techniques for supervised learning as described earlier in as for scenario 1 to 10 as one of the earlier lectures in this course. Cluster analysis has many synonyms like clustering, conceptual clustering, clustering techniques, clustering methods, etc. Cluster analysis is the task of grouping a set of objects in such a way that objects in the same group called a cluster are more similar, in some sense, to each other than those in other groups. Cluster analysis can be achieved by various algorithms that differ significantly in their understanding of what constitutes a cluster and how to efficiently find them. There are possibly over 100 published clustering algorithms. Typically, clustering algorithms are dependent on several hyperparameter settings, as for all machine learning techniques. Potentially, these parameter settings can also be automated based on separate learning processes. The default is to preset them, but they can also be learned theoretically. So let's look at a few examples of hyperparameters that may need to be specified for clustering algorithms. So of course, one important parameter is the number of clusters. Several algorithms need that to be predefined. Also, the number of features used to describe instances is of course important, but that's of course general to all machine learning algorithms. Type of distance measures to employ is a crucial thing. For certain methods, density is a concept. So, and one approach there is to set up some threshold for maximum distance between instances as a criteria for being dense, and also the number of instances that have to satisfy such a density threshold. But there can also be alternative density threshold measures. But that's also rather general for most machine learning algorithms. Many times you need to specify how many sessions for inspection of the data set that you would allow. Distance metrics have been described in the lecture on instance-based learning, but has also a very crucial role in cluster analysis. A distance metric or measure or function is typically a real-valued function that quantifies the distance between the two objects. Also said in the earlier lecture, but I would like to repeat it here again, is that distance metrics and similarity metrics have been developed more or less independently for different purposes. But usually specific similarity methods are intuitively inverses of corresponding distance and can therefore be transformed into each other. So we have then in the earlier lecture also exemplified with two categories of matrices that are pretty common. So either there are matrices in a normed Euclidean vector space, like Minkowski distance and its specialization, Manhattan Euclidean Chebyshev distances. We can also have the cosine measure. But we can also have matrices that can work on overlapping elements in other kind of data representation, not necessarily feature vectors. So they have a Levenstein distance for text, we have the Jacquard similarity for sets, and we have the Hamming distances for binary strings. So, as there are so many as 100 or more published clustering algorithms, these clustering algorithms can themselves be clustered in many ways. And you find in the literature very many ways of doing it. So for this lecture, I'm just choosing one of these ways of categorizing the clustering algorithms. And the categories I've chosen as most natural are partitioning-based, hierarchical-based, density-based, grid-based, and model-based. And as you can understand, all these hundreds of clustering algorithms can then be associated with any of these categories. Many times there are borderline cases, so sometimes one kind of algorithm could, depending on perspective, be viewed as one category or the other. But more or less, I would say that the well-known algorithms, at least those I know of, could be reasonably well classified according to this model. Let's start with partitioning-based clustering. So partitioning algorithms are clustering techniques that subdivide the data sets into a set of k clusters. And this number k for this kind of normally have to be preset. A majority of partitioning algorithms are based on the selection of prototypical instances, or synonymously centroid instances. These algorithms may be termed then centroid clustering techniques, so we can say it's a subcategory. In this approach, the selection of centroids are iteratively optimized and instances are iteratively reallocated to the closest centroid to ultimately form the resulting clusters. The result can be illustrated in a positioning of the data space, as we did for another purpose in instance-based learning, in a form of Voronoi diagram. You can see one such diagram to the. So properties of this argument: the target number of clusters is k, need to be preset, and of course the setting of that parameter is very important. Also, the initial seeds of these means or centroids have a strong impact on the outcome of the algorithm. There is some evidence that partitioning may perform better than others, like hierarchical approaches that we discuss later, because the clusters they produce are kind of have a better fit or are tighter than clusters produced by other methods. There are a series of algorithms of this class, but the most important and also oldest approach is k-means clustering, and we will discuss this in a little more detail. Partitioning-based clustering is here exemplified by the approach in the k-means algorithm. And actually, k-means algorithm is also an instance then of the subcategory centroid-based clustering. So the goal is to partition n instances into k clusters. So I'll start with selecting k instances out of the instances in the data set and allocate these as the initial means or centroids or prototype, terminology varies, and there are some motivation for all these terms. The distance is calculated between each of these means or centroids to every other instance. Typically, in the k-means algorithm, or originally at least, a Euclidean distance is applied. Then, the next step, when that has been done, you associate all the instances to the closest means, according to the closest mean, according to the calculation. And what you got then is a division of the total set in subsets. And we let these subsets that you get at this point constitute the initial clusters. So this you can see below in the example when we got this first partitioning of the data set in subsets. What happens then is that we redefine the means. And now you can understand why we also use the term centroid. It's because in mathematics there is a way of taking a lot of points in a space and calculating the most central concepts based on all central object based on all the data points. So this is now done. So we take all the instances that happen to be in one of the original cluster and calculate from that set the centroid of those according to traditional definitions of centroid. So this means you get a new mean or new central point for each of the initial clusters. But then you also, for all instances, recalculate the distance from all of the instances to the newly computed centroids. And this means that in this step, it can happen that the instances change cluster membership, which of course is a nice feature of this, because in a way we can revoke earlier less optimal choices. So then all of this is iterated many times until we reach stability, in the sense that the centroids do not move between these iterations, and then the algorithm typically stops. Let's now turn to the second type of category of clustering techniques, hierarchical-based clustering or hierarchical clustering techniques. So this is a kind of technique which seeks to build a hierarchy of clusters, not only one layer of clusters, but rather what was earlier mentioned in some of the lectures, like a taxonomy. So the results of the hierarchical clustering process is usually presented in what's called a dendrogram. And you can see to the upper right here on the slide, you can see a dendrogram that is related to an original set of instances depicted in the plane. And as you can hopefully infer, the structure of the dendrogram is based on the proximity or distance between the instances in the plane, in the example. So properties of hierarchical clustering. It does not assume a particular value of k as needed by the k-means clustering, so you don't need to specify that. The generated tree may correspond to a meaningful taxonomy, concept hierarchy. So from a domain modeling point of view, it's a nice technique. What you need is a distance matrix to compute the clustering steps. Or let's say you need two kinds of matrices. Actually, you need a distance matrix between instances, and you need what's called a proximity matrix between the clusters. But we will come back to that in the next slide. Initial seeds have a strong impact on the final results, as assignments cannot be done iteratively. So in a way, this algorithm is more sensitive to the kind of local decisions taking during the process. Actually, also this technique is very sensitive to outliers. It's another property. These slides give you a more detailed, very detailed actually, example of a dendrogram. That kind of diagram that shows the hierarchical relationships between objects. Actually, a dendrogram is a taxonomy. It's a graphical version or form of a taxonomy. It's very common that a hierarchical cluster can output this kind of structures. And of course, the role of the diagram is to work out the best way to allocate the objects to clusters. Let's look a little closer to hierarchical-based clustering. This kind of clustering can proceed in two ways. Agglomerative fashion, which is a bottom-up approach, where each observation starts in its own cluster. So exactly in the beginning, you have as many clusters as you have instances. And then through the process, pairs of clusters are merged as one moves up the hierarchy. Divisive fashion, where it's a top-down approach, where you start with all observations or instances in one cluster, and then and then you split that cluster recursively as you move down the hierarchy. And splits and merges are typically performed based on a proximity matrix between clusters. And actually here it's important to understand that there are two concepts of distance here. So first you have the basic distance between instances. So you can say for this kind of system, you start with a distance matrix between the instances. But then it's the habit in this kind of approach that you want to abstract a little. So therefore you want to calculate also not only the distances between instances, but somehow the proximity or distance between clusters. And it's actually a very simple relation, because if you have a distance matrix, given all the distances between the instances involved, then you can create a proximity matrix, which is the term used, between the clusters by taking, for each cluster, you take the average, the two clusters you want to compare, you take the average of the distances between the distances in the two clusters. So actually the proximity matrix is an abstraction based on the distance matrix. The proximity matrix is then recalculated in each step of the algorithm, because the distance doesn't change. So the distance matrix is the same, but because during the process the candidate clusters shift, we need to calculate the proximity matrix in every step for each new setup of candidate clusters. In general, all the steps in this algorithm, the merges and splits, are determined in a greedy manner, which has the effect that you can have the risk of not reaching a global maximum. We have discussed this earlier. All techniques that are greedy, that take local decisions that cannot be revoked or reconsidered, then there is this risk. So to the right, you can see simple examples where you have a number of instances, but these instances are then grouped into these 5 clusters, and then you can see that the proximity matrix is then a matrix with the clusters on as rows and columns, and you have this calculated value of proximity based on the instant distances in the elements of that matrix. Now we turn to the third category of clustering techniques that is termed density-based clustering. So density-based clustering is a clustering technique which groups together instances that are closely packed together. Instances with many nearby neighbors, marking as outliers instances lie alone in a low-density regions whose nearest neighbors are far away. So properties of this kind of algorithms are that clusters are dense regions in the instance space separated by regions of lower instance density. A cluster is defined as a set of connected instances with maximal density. So this kind of algorithm does not need a predefined target value for a number of clusters, but needs definitions for distances, for reachability, and density. It can discover clusters of arbitrary shape, and it's pretty insensitive to noise. So there are many advantages here. We will describe this technique a little more concretely in terms of the approach taken in one of these algorithms called dbScan. So let's now go through one of these algorithms called dbScan, a density-based approach. So the instances are classified in this case as core instances, reachable instances, and outliers. A core instance has a minimum number of instances within a threshold radius. An instance is density reachable from another instance if it's within a threshold radius from the core instance. An instance is density connected to another instance if both instances are density reachable from a third instance or if they are directly density reachable from each other. All instances not reachable from any other instance are considered as outliers, could possibly be noise. If P is a core instance, then it forms a cluster together with all instances that are reachable from it. Each cluster contains at least one core instance. Non-core point can be part of a cluster, but they form its edge. All points within the cluster are mutually density connected. If a point is density reachable from any other point in the cluster, it's part of the cluster as well. So here we can see that we build up the clusters through the core instances and then through the density reachable property. And the two important parameters here is of course the threshold radius, but also the minimum number of instances that must be within the threshold radius in order for an instance to be counted as core. So in the example to the right, you can see that the red instances are core instances because the area surrounding these in a epsilon radius. The threshold radius contains a specified number, minimum of 4 points in this case. Because they are all reachable from one another, they form a single cluster. B and C are not core points, but are reachable from A, and thus belong to the cluster as well. But the point N is a point that is neither a core point nor directly reachable, and is not therefore considered part of the cluster. Finally, we will look a little more closely at something called grid-based clustering. So grid-based clustering, you quantize the instance space into a finite number of cells, hyperrectangles, and then perform the required operations on the quantized space. So typical steps in this kind of algorithm is to find a set of grid cells, assign instances to the grid cell, and compute densities of the cells. Eliminate cells that have densities below a certain threshold. Form clusters from adjacent cells based upon some objective optimization function. So So actually one could say that grid-based clustering is density clustering of a certain kind, also with this introduction of this kind of grid structure. So finally, I want to say something about model-based clustering, even though it doesn't really fit into this week, because, as you know, the title of the whole week was Inductive Learning in the presence of weak or absent domain theories. So model-based clustering is actually a clustering technique where we have some model or background knowledge or theory about the domain from which the instances of the datasets is harvested. So this model can more or less extensive, but can in all cases to some extent guide the clustering process. The basic clustering process that we start from can in principle be any extension to one of the other clustering approaches we discussed earlier here. If the domain knowledge is some statistical information about the distributions for kinds of instances involved, one can call this kind of clustering technique distribution-based learning as a category of its own. So, example of a distribution-based clustering scenario is where you have sample instances that arise from a distribution that is a mixture of two or more components. And two components here means, of course, two types of instances. So each type of instance is derived by a density function and associated probability or weight in the mixture. The mixture is, of course, the whole, the heterogeneous data set with these kinds of instances. In principle, we can adopt any probability model for the components, but typically we will assume that they are p-variant normal distributions. And of course, what we end up with here is that each component in the mixture becomes what we call a cluster. So this was the end of this lecture on cluster analysis. Thanks for your attention. The next lecture and the last one for this week will be the tutorial regarding the assignments for the week. Thank you. Bye.